In this video, I'd like to cover another picture for the SVD, and this is called the 4 spaces picture. We know that the matrix A can be decomposed to be U sigma V transpose. But this also means that A multiplied by V is equal to U multiplied by sigma. This can be rewritten as A multiplied by a matrix V which has some columns V1, V2 up to Vn, and assume for now that we are talking about a square invertible matrix A with dimensions n by n. So A multiplied by this is equal to some other orthogonal matrix U having columns U1, U2 up to Un multiplied by another diagonal square matrix sigma. Here we have sigma 1, sigma 2 up to sigma n. This again means the following. We have A multiplied by V1 is equal to sigma 1 multiplied by U1 because we have zeros here. So the first column of this multiplication is equal to sigma 1 multiplied by the first vector plus 0 multiplied by the second vector and so on. So this is equal to sigma 1 U1. Also, AV2 is equal to sigma 2 multiplied by U2, and in general, AVI is equal to sigma I UI. We also know that the matrix V is an orthogonal matrix, so the magnitude of VI is equal to 1, and also we know that V1 is perpendicular to V2 is perpendicular to V3 and so on, and the same applies for UI. The magnitude of UI is equal to 1, and all the vectors U are perpendicular to each other because those two matrices are orthogonal rotation matrices. Now we can use those equations right here to get a very interesting interpretation. Remember that when you multiply a matrix by a vector, the result vector will be a linear combination of the columns of the original matrix A. This means that the result vector will lie in the column space of the matrix A. So all the vectors U right here belong to the column space of the matrix A. Now what about those vectors V? You know that if you multiply A, V, you can have two results. If the vector V lies in the null space of the matrix, then AV will be equal to 0. This is the definition of the null space of the matrix. On the other hand, the vector V can lie in the orthogonal space to the null space, that is the row space. So if V lies in the row space of the matrix, then A multiplied by V will not be equal to 0. It will be equal to some other vector in the column space of the matrix because we are having a linear combination of the columns of the matrix A. So if V lies inside the null space, we will have this result. If we have V lying in the row space, we will have AV not equal to 0. A general vector V might have a component in the null space and another component in the row space, and this means that part of this vector will be taken to 0 and the remaining part will be taken to the column space. But assume for now that we are talking about an invertible matrix. If a matrix is invertible, then there is no null space of this matrix and all the vectors V will belong to the row space. If you don't remember the relation between the 4 high spaces, I highly recommend that you go and revise the videos on the relation between the 4 subspaces because we will be dealing with those subspaces a lot during handling the SVD. So again, for this non-singular case, we have the following. Here we have the row space of our matrix A. The row space in general is perpendicular to the null space of the matrix A. Here we have the column space of the matrix A, and here we have the left null space, the null space of A transpose. So this is the null space of A, this is the column space of A, this is the row space of A, and here we have the null space of A transpose. Now, suppose we are talking about a two-dimensional case such that A multiplied by V1, V2 is equal to sigma 1, U1 and sigma 2, U2. Then we know that AV1 is equal to sigma 1, U1 and AV2 is equal to sigma 2, U2. Now, both V1 and V2 belong to the row space if the matrix is non-singular. So we have two vectors in the row space maybe this vector v1 and this vector v2, and they are unit vectors and perpendicular to each other. When you operate on those vectors using the matrix A, you get some vectors in the Coulomb space. You don't get the zero vector because you don't have any null space for your matrix. So if you operate by the matrix A right here, you get sigma 1 u1 and sigma 2 u2. So you get here, let's say this is sigma 1 u1 and this might be sigma 2 u2. Now you know that u1 and u2 are perpendicular to each other, and so sigma 1 u1 and sigma 2 u2 will also be perpendicular to each other. In general, in the SVD, we do order the singular values such that sigma 1 is greater than sigma 2 up to sigma n, sigma 2 is greater than sigma 3, and sigma n minus 1 is greater than sigma n. This is similar to what we have done in the BCA, where we ordered the eigenvalues in descending order. So you can actually think of the SVD decomposition as follows. For the SVD, you are looking for the matrix U and the matrix V. This means that you are looking for V1, V2, and U1, U2. So you are looking for some perpendicular bases of the row space that when multiplied by the matrix A will result in another perpendicular basis in the Coulomb space. Remember that multiplying by a matrix in general does not preserve the angles. So if you get any two perpendicular vectors in the row space, let's say y1 and y2, then if you multiply those by the same matrix A, there is no guarantee that you will get two perpendicular vectors in the Coulomb space. You might get this and this, for example. And also note that you can actually have an infinite number of bases for the row space. You can have those, you can have those. You can have this and this, for example, as bases for the row space, and so on. And actually, I didn't intend this y1 to be parallel to v1, so I might change those to have a different basis, like this, maybe, and so on. So you get the idea. There is an infinite number of bases for the row space, but the SVD is looking for a very special basis right here, those two vectors, that when multiplied by the matrix A, the resulting two vectors will still be perpendicular to each other, not having this problem right here. Later on, we will find out that the SVD will still work even if the matrix was singular and even if the matrix was a rectangular non-square. But before that, I still want to give some more intuition about the four spaces picture.